Hello, this is our group project for IE 4305, Engineering Decision Making with Data Using Python, Spring 2025. Predicting airline arrival delays using machine learning. Our group members are Syed Ali, Zachary Beals, Gabriel Mireles, Tracy Nguyen, Jasmine Pancratz, Paxton Roden, Omar Soldevilla, and Felton Walton.
Today I'll be discussing a project focused on predicting flight delays using machine learning. Flight delays are a persistent issue in the aviation industry, not just from a passenger convenience perspective, but also due to their massive financial implications. According to the FAA, delays cost airlines around $22 billion each year. These costs include operational disruptions, staffing inefficiencies, and misconnections. Additionally, a 2008 report from the Joint Economic Committee revealed that delays totaled over 1.8 million hours annually for domestic flights, contributing to major economic impacts. These delays do not only affect airline operations, but also significantly impact customer satisfaction and logistics on a national scale. For this project, we gained hands-on experience applying three machine learning models: multiple linear regression, random forest, and k-nearest neighbor. The purpose was to evaluate how well these models could predict flight arrival delays based on a dataset of historical flight data. The primary goal of this study was to explore how machine learning algorithms can be used to analyze flight delays data and identify contributing patterns. By comparing the performance of these models, we aim to determine which methods are most effective at forecasting future delays. Ultimately, this research helps inform airlines and airports on better strategies to reduce delay frequency and improve operational efficiency.
The experimental setup for this project consisted of two sections: obtaining the data and then putting the data through the pre-processing phase. The dataset that was used for the forecast models in this experiment was the flight and arrival data of American airline planes coming into DFW Airport over the course of 24 hours. This dataset had a total of 17 predictors in the form of data columns. 5 of these data columns were categorical, while 12 were numerical, with each data column having a total of 433 samples. Then, in the second part of the experimental setup, the data was put through the pre-processing phase, which consisted of cleaning and encoding the data. For cleaning the data, all data columns were removed with the exception of the flight number, origin airport, scheduled elapsed flight time, and actual elapsed flight time. The reason behind doing this was because many of the data columns were either redundant or irrelevant to this project and would have only cluttered the results of the forecasting models. Once the data was cleaned, the origin airport data column was then encoded for ease of analysis, and also, as the initial data was text, it needed to be numerical in order to be compatible with the forecasting model code. For this experiment, 3 different forecasting models were selected to be tested. The first forecasting model is multiple linear regression, or MLR for short, which models a relationship between a continuous dependent variable and 2 or more independent variables by fitting a linear equation to them. The next forecasting model used was random forest, which builds a forest of decision trees and takes an average of their results for a more accurate prediction. The last forecasting model used was k-nearest neighbor, or KNN for short, which predicts a value by averaging the target values of the k closest points or neighbors.
Multiple linear regression and how it works. Multiple linear regression, or MLR, is a statistical method used to model the relationship between one dependent variable and multiple independent variables. In our project, we used MLR to predict flight arrival delays based on factors like where the flight originated from and the flight duration. The model works by finding the best fitting line, or more accurately, the hyperplane, that minimizes the difference between the predicted and actual values. This line is determined using learned coefficients, which represent how much each independent variable contributes to the prediction. Once trained, the model applies these coefficients to the new data in order to make new predictions. However, in order for MLR to work properly and give the best results, several assumptions must be met first. First is linearity, which means that the relationship between the inputs and the outputs must be linear. Second is normality of residuals, which means that the prediction errors should be normally distributed. Third is homostochasticity, which means that the residuals should have a constant variance of errors across all made observations. And lastly, no multicollinearity, which means that the independent variables shouldn't be too strongly correlated to each other. If any of these assumptions are violated or not met, it could lead to biased and misleading results of the model.
Random forest. The random forest algorithm works by using the bootstrap sampling method, which creates multiple random subsets of the original training data using sampling with replacement. And these subsets are used to train a decision tree. In other words, after creating the subsets for a decision tree, it puts all of the original training data back into the pot before creating new subsets for the next one. After sampling, it trains the trees. Decision trees have a flowchart-like structure. Each split is the result of a test on a random subset of features, and the trees predict real valued numbers. The final prediction is calculated with the following equation, which is the average of all decision tree predictions. Here we have a visualization of how the data is split and a decision tree is made. The internal nodes denote a test on the data set, and branches represent the outcome of the test. After all of the randomized subsets are generated, a terminal node with a real valued number sits at the end of each path on the decision tree. The prediction for that decision tree is the average of the terminal nodes. Decision trees can become very complex when working with real-world data, as you can see here. This is one of many decision trees generated by our random forest model.
So what is KNN and how do we use it in our project? So KNN works by storing all the training data and making predictions only when needed. When a new input comes in, it looks at the K closest points from the training set and then predicts the output by averaging their values or taking the majority vote. The number K is something we choose ourselves. Common choices are 3, 5, 10, or even 20. A smaller K focuses on more local patterns, while a larger K gives more smoother, more general predictions. To figure out which neighbors are closest, the algorithm uses a distance metric. The most common one is the distance we can see on the slide here, which measures the straight line distance between points. The formula shown here sums the squared differences for each feature and then takes the square root. On the right, we can see the plot, which shows how this works visually. The green stars are test data, and the blue stars are predictions based on the nearest training points, which are shown as blue dots. The arrows connect the test point to its closest neighbors that were used to make the prediction. So this slide here explains two key metrics we use to evaluate how our model is performing: R squared and root mean squared error, better known as RMSE. Starting with R squared, it tells us how much of the variation in our target variable can be explained by the input features. So if we have an R squared value closer to 1, that means our model is doing a good job explaining the data. It's a common way to measure how accurate a regression model is. Then there's RMSE, which looks at the average size of errors between the predicted values and the actual values. What's helpful about RMSE is that it is the same units as our target, in our case, minutes. So it's easy to interpret how far off the predictions really are. In general, the better performing model will have a higher R squared and a lower RMSE. which means it is more accurate and makes smaller prediction errors.
So here's a MLR-QQ plot. When using this plot, we want to see if the residuals are normally distributed or not. And based on our results, our residuals were not normally distributed because there are signs of heavy tails and left skewedness. So if we take a look on the graph here on the right, we see that the left tail, a lot of the plots do not follow along the red line. Similarly, the right tail does not follow along the line. And that gives us a conclusion that MLR would not be a good fit as a model for our dataset. Here we have our random forest scatter plot. So as we can see, most points fall on the diagonal line of y equals x, so that's what we want it to do, which gives us a conclusion that the model's predictions are well aligned with reality. This is our KNN scatter plot. Most points fall on the diagonal line of y equal x, so it's very similar to a random forest. For comparison, as we can see, random forest does follow along the line of the diagonal line better compared to the KNN data points. So the model's predictions for KNN are well aligned with reality, but it's not as close of a fit as random forest is.
Results. Multiple linear regression. R squared value was 0.99. The Brusque-Pagan test shows presence of heteroscedasticity. The Shapiro-Wilk test show lack of normal distribution. Tests indicate results are invalid and a nonlinear model would be better suited for our data. Random forest. Accuracy score of 0.937. Predictions were off by about 14 minutes on average. This was the better performing model. K nearest neighbor. Accuracy score of 0.708. Predictions were off by 30.01 minutes on average.
To conclude our project, we saw how machine learning can offer real-world solutions to long-standing industry problems, in this case, flight delays. By applying data science to historical flight records, airlines could better predict potential delays and make preemptive adjustments, which can greatly reduce customer dissatisfaction and operational losses. Our models focus on using actual versus scheduled flight time data to make predictions. What we found is that machine learning doesn't just help identify patterns, it helps us act on them in a meaningful way. For example, with more accurate predictions, airlines can improve scheduling, allocate staff and resources more efficiently, and even optimize fuel usage and crew assignments, leading to more cost effective and reliable services. Even though we tested 3 different models, this project also highlighted how important it is to choose the right model for our dataset. Assumptions, data behavior, and the context of use all matter. And in our case, the model that best fits was random forest. Some highlights. Our project evaluated 3 models: multilinear regression, random forest, and K nearest neighbor. The goal was simple: to determine which model best predicts flight delays using a dataset based on scheduled and actual durations. While MLR and KNN gave us some insight, random forest stood out. It had the highest accuracy of 93.7% and the lowest average error of 13.99 minutes. That means random forest not only made reliable predictions, but did it closer to real life outcomes, making it the best choice for future predictive models in this context. Our project shows the real power of machine learning, not just in theory, but in how it can improve everyday systems like air travel. With better models and data, we can help industries minimize losses and enhance customer satisfaction and make smarter, faster decisions. These are some of our references. Thank you for listening. We are happy to answer any questions.